So what I wanted to say is that indeed semi-definite programming and real algebraic geometry play a central role in the topic I want to discuss. And it's also closely related or tight connections with distance matrix completion problem and PSD matrix completion problems, which I will only very superficially touch. But at least I think this is nicely fit to this very wonderful thematic program that you are now organizing at the Fields Institute. So let's get started. Today, I want to give a gentle introduction to polynomial optimization. So when I received this nice invitation, I was asked that the first lecture should be accessible to a broad mathematical audience. So indeed, it will be a gentle introduction. And maybe I should apologize to all the experts in the virtual room who may know most of what I will say today, but this is meant to a broader audience of maybe less expert people than many of you are, but nevertheless, I hope you will enjoy the lecture. So what is polynomial optimization? Well, it is a class of optimization problems where you want to optimize. In this talk, we are going to minimize a polynomial function over a region K, which is defined by polynomial inequalities or equations. So what is specific in this problem is that all objects, the objective and the constraints, are polynomial functions. So of course, this is a very special instance of nonlinear, non-convex optimization, which is an enormously broad field. But what is specific here is that this presence of polynomials and this algebraic structure can be exploited to design dedicated methods that may be able to reach more than in the general setting. And as we will see, one will be sometimes able to reach the global minimum of the problem, while in general, in nonlinear optimization, methods such as first order methods can only reach local optima. So the specificity of polynomial optimization is to design a technique which may sometimes reach the global minimum. So when talking about minimizing a function or a polynomial, this is the same thing as trying to find the largest lambda, scalar lambda, so that f minus lambda is non-negative over the feasible region. So very close by, we have this question of testing non-negativity of a polynomial. So I want to start with, give a few instances of where this question of non-negativity arises and how difficult it is. And as we will see, it is a hard question. So the first setting is the most simplest setting is when we would have the unconstrained quadratic case. So where we want to minimize when we want to decide whether a quadratic form is non-negative or full space. And this is an easy thing to decide because this quadratic form is non-negative over the full space precisely when the matrix M is positive semi-definite. And this can be tested in polynomial time using Gaussian elimination, for instance. But as soon as we relax one of these two words, either unconstrained, so if we look at the constraint case instead, or we relax quadratic, we look at higher degree polynomials, then the problem becomes very quickly hard. So as a first such instance, we can look at testing whether a matrix is copositive. So a matrix M is copositive if the same quadratic form is non-negative on the non-negative orthon. So now instead of looking at non-negativity over the full space, you only look at non-negativity over the non-negative orthon, and this is a hard problem. So another way to rephrase this is to encode the non-negativity over the space that we look at. So instead of having xi, we just replace xi by xi square, and then the non-negativity will be encoded automatically. And then we obtain the quartic polynomial here, which we are asking whether is it non-negative or the full space. And this is the same thing as testing whether the matrix is copositive, and this is hard. Another hard instance is obtained when looking at testing convexity of a polynomial. This is also hard already when the polynomial f is convex. And you can reformulate this via asking whether the Hessian is positive semi-definite. And now we can make this polynomial in x and y by introducing a new set of variables y, and f is convex if and only if this newly created polynomial in x and y is non-negative over the full space, and this is a hard problem. Yet another class of instances that we can look at comes from distance geometry, so the center of this thematic program. So here we have a collection of objects, and we have only some measurements between some pairs of objects, but we would like to reconstruct the locations of the objects from these partial measurements, from these partial distances. In other words, we have some distances, dij, only for some pairs, which can be modeled via as the edges of a graph. And we ask whether it's possible to find locations, so vectors u1, un, in some k-dimensional space, whether the dimension k could be fixed, equal to 1, 2, 3. And the distances should be realized by the Euclidean distances between the vectors. So this is a problem again, which of course can be reformulated as testing whether a certain semi-definite program admits a feasible solution. So here we just introduce the matrix X as the gram matrix of the locations which we are looking for. And then so these constraints about the distances, about the locations, translates into these constraints about the entries of the matrix. So matrix should be positive semi-definite. And to encode that the vectors you look for should be in the k-dimensional space, and so you translate this by saying you want to find a solution to this SDP which has rank at most k. And as is well known, this is a hard problem, testing existence of feasible solutions of low rank. Another possible reformulation of this is to formulate this as a polynomial optimization problem. We create this polynomial P from the data. So this polynomial has variables xi, h, where I runs over the n locations, h runs over the k possible dimensions. And we see that it's a sum of squares, so it's always a non-negative, and it's going to attain minimum value 0 precisely if the locations exist, and the global minimizer are going to give the location. So all these reformulations show that this is a hard problem, as was already shown long ago by Sachs. It's hard already if you restrict to dimension k equal 1, and when the distances are specified on the edges of a very simple graph, indeed the cycle, and Sachs gave this nice reduction to the partition problem. Yet another class of examples come from combinatorial problems in graphs. So here we have a graph, and there are two parameters of interest, the stability number and the coloring number. So the stability number, usually denoted alpha of G, that's the maximum cardinality of a set of vertices which are pairwise not adjacent, and such a set of vertices is usually called a stable set of the graph. And the coloring number is the minimum number of colors that you need to properly color the vertices, which means that if two vertices are adjacent, they should get different colors. So here on the Peterson graph, the 4 red vertices form a stable set. They are pairwise non-adjacent. They form a stable set of size 4, and that's the maximum possible. So the stability number is 4. And we have partitioned the vertices into 3 color classes. So color class corresponds to a stable set, and that's the smallest possible number. So the coloring number is 3. So these two parameters are hard to compute. And there is a very easy reduction due to Schrattal, which explains how to reduce the computation of the coloring number via a sequence of computation of the stability number of the Cartesian product of G with a sequence of complete graphs. So in a sense, this shows very easily, directly, that the stability number is a very crucial parameter to understand. So I next want to show you a few polynomial optimization formulations for the stability number. So the most simple one, probably the most well-known, is the basic binary formulation, where we have variables xi, 1 for each vertices, and supposed to take values 0, 1, because this indicates whether the node, the vertex, is put in the stable set or not. So the binary condition, you just model it by saying that the xi square should be equal to xi. And here this edge condition says that if two nodes form an edge, then the product of the variable should be equal to 0, because you can take at most one of the nodes in the stable set. And then the size of the stable set is, you model it by adding up the variables. Another formulation which is well known is due to Motzkin-Strauss, which reformulates the computation of the stability number as a continuous problem, where you want to minimize a quadratic form. So here the matrix involved is the identity plus the adjacency matrix. So you minimize this quadratic form over the standard simplex. So all non-negative vector summing up to 1. Again, one can encode non-negative variables by simply replacing them by xi square. And in this way, we get a reformulation for the stability number via minimizing this quartic form over the unit sphere. Yet another way to reformulate this as conic optimization over the copositive cone. So as these formulations show, the stability number can be reformulated via various ways as polynomial optimization over the cube, over the simplex, over the sphere, or using the copositive cone. And we will return to this topic in the third lecture. But let me very briefly mention how to get very easily an upper bound for the stability number and a lower bound for the calorie number, which is well known to you, but nevertheless. So the idea is, if we have a stable set, we encode it by a vector x, which is binary, where we put a 1 if the node is in the stable set and a 0 otherwise. Then we append one entry equal to 1 to this vector, and we create the matrix x, which is the outer product of this vector. In this way, we get a matrix which is positive semidefinite and entry-wise non-negative. And now we can make this semidefinite program, which was introduced by Lovas and which gives the theta number. So the objective is just summing up the entries corresponding to the starting entry variables xi. And we have, this is the conditions which exploit the fact that the variable should be binary, and here these are the edge conditions. We can strengthen this parameter by adding non-negativity. As observed, the matrix X we have created is not only positive semidefinite, it's also entry-wise non-negative. So if you add non-negativity, you get a strengthening of the theta number known as the theta prime of the graph. So in this way, we obtain parameters. So alpha is at most theta prime, is at most theta, is at most a calorie number. So theta prime and theta can be computed via semidefinite programming. So how to get stronger bounds? So this is what I want to explain, and we are going to see that how to do this for the most general setting of polynomial optimization. But one small observation here is that actually, in order to define this theta parameter, what we did actually is lift the problem in higher dimension. Instead of staying in the space of the n variables, x1, xn, which correspond to the vertices of the graph, which is the level where the question was posed, we lift the problem to higher dimension by considering pairwise products of variables. And this is one of the basic ingredients in order to construct stronger and stronger bounds. So let me just briefly highlight a few of these key ideas that are employed in order to get stronger bounds. So as just mentioned, the first key idea is to lift the problem to higher dimensional space. So instead of staying in the space of the original variables, we add new variables which model products of original variables or triples, product of triples of variables, and so on and so on. A second key idea is to replace non-negativity of polynomials, which is a hard condition. We replace it by a proxy, which is easier to test. And this proxy is using sums of squares of polynomials. And the key fact is that sums of squares of polynomials can be modeled using semi-definite programming. So let me briefly recall how this goes. So I expect that most of you know how this goes, but this is very simple. So let me recap how this goes. So if we have a polynomial f, And we want to understand whether it's a sum of squares of polynomial, yes or no. So first of all, it better have an even degree, 2D, otherwise it's not possible to write it as a sum of squares. So suppose f is a sum of squares of polynomial pi of x, and we want to find this pi. So a very simple idea is, let's write the polynomial pi of x as the inner product of two vectors. The first one is this vector pi bar, which contains the coefficients of the polynomial in the monomial base. And the second one in blue is the vector whose coordinates are is a monomial base. So there you put all the monomials in the monomial base. And then we can rewrite the pi of x square. Here we write it as, first we put the monomial base first in a product with a vector of coefficients, and then we put the vector of coefficients in a product of monomial base. Then you pull out this vector of monomial base, so the blue vector, you pull it out of the summation. And in the middle, what remains is the sum of these outer products, pi transpose. So this sum of outer products gives you a positive semi-definite matrix, and conversely, any positive semi-definite matrix looks like this. So what we obtained is that f is a sum of squares if and only if there exists a matrix M, positive semi-definite, which satisfies this polynomial identity here. And now it suffices to finish up. We have a polynomial identity, so we just equate the coefficients of the polynomial on both sides. So here we have f alpha, and here we should find out what is the coefficients of x alpha, and this is what we do in this last formulation, which to summarize, f is a sum of squares of polynomial if and only if we can find a matrix M, positive semi-definite, which satisfies this bunch of affine equations, and this is an instance of semi-definite program. So a very brief recap on semi-definite programming, so which I put in comparison to linear programming, which is probably the most well-known. So in both settings, what we want to do is to optimize a linear objective function. In linear programming, we want to optimize these linear objective functions over a feasibility region, which is a polyhedron, which means that we have a vector variable x satisfying a certain number of equations, affine equations, and x constrained to lie in the non-negative ordinate. On the other hand, in semi-definite programming, what we have is a matrix variable x satisfying again a bunch of constraints, affine constraints, but now the matrix variable x is constrained to be positive semi-definite. So here is how the typical feasibility region of a linear programming looks like. It's a polyhedron. And here is a typical region of a semi-definite program. It's a spectrahedron, and it's a convex non-polyhedral region in general. And the key thing is that there are efficient algorithms to solve linear programming and to solve semi-definite programming up to any precision. So there are some subtleties when going from LP to SDP. Maybe let me mention one such subtlety. So in linear programming, if you start from rational data, then there is always an optimal solution, which is going to be rational valued, and the bit size of the optimal solution is polynomially bounded in terms of the bit size of the input data. This is not true anymore in general for semi-definite programming, because there are very simple instances of semi-definite program with rational data, but yet there is no optimal solution which is rational valued. So this is why you cannot do away with this precision here. You cannot solve it exactly in general. And of course, this is a very broad field. There is much more to say, but let me just mention that you also have to be careful that you know an inscribed ball in the feasibility region, and you also know a ball around the feasibility region. And the complexity is going to depend on the radius of these two balls. And the reason is that you want to make sure that the optimal solution is not going to be too small, or it's not going to be too large. I don't want to say much more about this. One more thing I want to say is that on the theory side, there is still a very interesting question which is still open. Namely, it's what's the exact complexity of testing the feasibility of an SDP. So if you have rational data, and we want to decide whether there is a PSD matrix which satisfies the given affine constraints. So the exact complexity is still not known. What is known is that the problem belongs to NP if and only if it belongs to co-NP. What is also known is that the problem belongs to P, so it's polynomial time solvable when fixing either N, the metric side, or M, the number of constraints. And finally, let me mention that there is a well-developed duality theory, which holds actually in the more general setting of conic programming. But again, we need to be a bit careful about, you need some strict feasibility conditions in order to ensure that there is no duality gap. Okay, so I think now after this general introduction, let me start, let me move to what is a general approach to polynomial optimization. So this on top, you have again this polynomial optimization problem where we want to find the minimum value taken by a polynomial f over a feasibility region defined by polynomial inequalities. So this is a hard problem, and the strategy is to approximate it by a hierarchy of convex, in fact, semi-definite relaxations, which will be constructed using either sums of squares of polynomials or the dual theory of moments. So this general approach was started in early work by Shores and Nesterov, and developed in full swing by, in particular by Jean-Bernard Lasserre and Pablo Parrilo from the year 2000. And there is now a very broad literature on this, and I will only now touch a bit of the main developments. So as mentioned, there are two dual sides to the story, and I will describe them in turn. And the point is that each side, so either the sum of square side or the moment side, each side will give additional complementary information about the problem. So let's start with the sum of squares approach. So here is again the rationale. Testing whether a polynomial is non-negative is hard, but one can test the sufficient condition whether f can be written as a sum of squares of polynomials using semi-definite programming. So a very quick recap, just to point out that actually this is really a relaxation. If we replace non-negativity by being a sum of squares, this is really a relaxation. So not all non-negative polynomials are sums of squares, and this was already known to Hilbert, who characterized in 1888 what are the pairs n, d, where n is the number of variables, d is the degree. So what are the pairs n, d, for which every polynomial in n variables and degree d even is a sum of squares of polynomials. And what Hilbert showed is that this happens only in three cases. The first case is a univariate case, n equal 1. The second case is a quadratic case, d equal 2. And the third case is the exceptional case of polynomials in two variables and degree 4. And in all other cases, there are counterexamples. So there are polynomials which are non-negative, but not sums of squares. So Hilbert, after that, posed what is known as a Hilbert 17th problem. So not every non-negative polynomial is the sum of squares of polynomials, but is it a sum of squares of rational functions? And this was answered in the affirmative by Artin in 1927, and this started the field of real algebraic geometry. So the first concrete, I think, example of a polynomial which is non-negative but not a sum of squares is due to Motzkin. So this is this Motzkin polynomial, so degree 6 in two variables, which is shown here. So we cannot hope to find a non-negativity certificate via sums of squares, but we can hope to find, I mean, we know there is a certificate via a sum of rational squares, and here is such a sum of squares. So if we multiply p by x squared plus y squared square, then we find a sum of squares. So this gives an explicit certificate of non-negativity for p. But we are minimizing a polynomial on a feasibility region K, where K is defined by polynomial inequalities. So we need positivity certificates over K. And here is a way to get a positivity certificate. Namely, what we can do is try to represent the polynomial as a conic combinations of the constraints which define the set K. So we try to write a polynomial as S0, where S0 is the sum of squares, plus the sum of Sj, Gj, where every Sj is the sum of squares. So it is clear that every polynomial in the quadratic module is non-negative over the set K. You could look at a richer set of certificates, namely those in the preordering generated by the constraints, where you look at, you try to express your polynomial as a conic combination of pair of products of the constraints. So you get a much richer set which contains a quadratic module. So this the quadratic module in the preordering actually allow to get a very rich class of certificates, which is sometimes sufficient. So these are these results of Schmidgen and Püttinach. So assume our feasibility region K is compact. Then what Schmidgen proved is that if F is a polynomial which is strictly positive on K, then F lies in the preordering. So then F will admit such a nice positivity certificate as a conic combination of pairwise product of constraints. The result of Schmidgen says that let's make a tiny small additional assumption on the set K. Namely, let's assume that we can find a radius R for which this equation R minus the sum of xi squared lies in the quadratic module. So this is simply saying there is an explicit ball constraint which lies in the quadratic module. And then what Püttinach showed is that if F is strictly positive on K, then F lies in the quadratic module. So this Archimedean condition is actually very easy to be satisfied, because by assumption the set K is compact. So if we know a ball, I mean, then there is a ball containing K. And if we know the radius of such a ball, then we can just add a possibly redundant constraint to the description of K, and we get a description of K which satisfies the Archimedean condition. And then it's enough to stay in the framework of the quadratic module. And from a computational point of view, this is much better, because we are involving only conic combination of the M constraints instead of conic combinations of the possibly 2 to the M products of constraints. So we will consider only the case when the semialgebraic set K satisfies the Archimedean condition. So if we want to design bounds that can be computed using semi-definite programming, the only additional thing we need to do is to restrict the degree of this sum of squares multiplier Sj. So we are going to, we pick an integer t, which is our degree bound, and we restrict to the case where all the summands will have degree at most 2t. So in this way, we can now define the bound of order t, so the SOS bound of order t, which we define as the largest lambda, scalar lambda, for which the polynomial f minus lambda lies in the truncated quadratic module. So the quadratic module truncated at degree 2t. So as argued, sums of squares can be modeled using semi-definite programming. So each SOS bound of order t can be computed via semi-definite programming. As the order t grows, we get bounds which are possibly better and better. And actually, they converge asymptotically to the minimum of f over the set K. So this asymptotic convergence follows directly from the positive Stellensatz, which I just showed you before in the previous slides by Püttinach. So this was the basis of the approach of Lasserre in his seminal paper. So so far I just explained how to use sums of squares to design a hierarchy of bounds, so the SOS bounds, for growing orders. And as we have seen, this hierarchy of bounds converges to the minimum of f on the semi-algebraic set K. And this sums of square approach is useful because it gives certificates for non-negativity. So what I want now to do is to describe the dual approach, so the so-called MOMt approach, which will give us additional complementary information, in particular about not only about the minimum value of f, but also about the minimizers, the global minimizers of f on the semi-algebraic set K. So let's start with from the beginning. So we start again with our polynomial optimization problem, which asks to find a point x in the semi-algebraic set K, whose f value is as small as possible. So now what we can do is every point x in the set K, we can model it by, we can view it as a measure, namely we model it by the Dirac measure at K. And then since we are minimizing, so instead of minimizing over the Dirac measure at x, we can minimize over a convex combination of Dirac measures at points in K. And this leads us to minimizing over probability measures on the set K. So in other words, we can reformulate our original polynomial optimization problem as a problem of finding a probability measure mu on K, for which the expected value of f with respect to this measure on the set K is as small as possible. So this is really a very easy derivation. And then, well, if we have a probability measure mu on K, we can consider the corresponding linear, this defines a linear functional L, which acts on the ring of polynomials. So namely, we just define L evaluated at the polynomial f, you just define it as the integral of f de mu. So, and now we can reformulate the original optimization problem as finding a linear functional L acting on the ring of polynomials, minimizing L of f, but we should restrict to those linear functional L which admit a representing measure on the set K. Well, this question of understanding which linear functionals have a representing measure on the set K is actually the classical MOMt problem, but it's a difficult problem. It's no surprise because we have, this is just a reformulation of our original hard problem. But what we can do is we are going to, instead of, we are going to replace asking for representing measure, we replace it by a necessary condition for this. And this necessary condition is that L should be non-negative on the quadratic module generated by the constraints that define the set K. So the next thing is just to observe that testing non-negativity of L on the quadratic module can actually boil down to a semi-definite program again. So there are two things to do. First, we should check that L is non-negative on every sum of squares as 0. In other words, L should be non-negative on all squares of the form p square. And this can be reformulated as asking that a certain matrix M of L should be positive semi-definite. This matrix M of L is known as the MOMt matrix of L. And it's a matrix indexed by monomials, alpha, beta. And the alpha, beta entry is L, evaluated at the products of the monomials x alpha and x beta. So maybe it's easiest is to read this line below the box. So L of p square is equal to, so just write p in its monomial expansion, it's the sum of p alpha x alpha square. You expand the product and you get sum of alpha beta p alpha p beta, L evaluated at the monomial x to the alpha plus beta. And then you see that using the definition of this MOMt matrix M of L, this is equal to the quadratic form with the matrix, whose matrix is M of L, evaluated at the coefficient vector of P. So in other words, L of P square is non-negative for all P, if and only if the MOMt matrix M of L is positive semi-definite. And this small calculus, you can do it the same for the other terms. You should also check that L is non-negative on every term Sj, Gj, where Sj is the sum of square. In other words, you want that L is non-negative on every Gj times P square. And this is equivalent to the MOMt, the localizing MOMt matrix, which is defined in this way. So you just plug in the polynomial inside here. And these are the localizing MOMt matrices, which should be all positive semi-definite. So the goal of these localizing moment matrices is to ensure that the support of the measure which we are looking for is going to be contained in the semi-algebraic set, which is defined by this polynomial Gj. So now we are ready to define the hierarchy of moment relaxations for our original problem. So we start with this reformulation in terms of existence of L having a representing measure. And then we replace it by the necessary condition for it, and we truncate in order to get programs that we can compute. So again, we fix the degree t, and we truncated degree to t, which means that the moment bound of order t is defined as minimizing L of f, where L acts on the space of polynomials up to a given degree to t, and L should be non-negative on the truncated quadratic module. And L of 1 is 1 is capturing the fact that you are looking for a probability measure, so total mass 1. And as just observed before, this can be reformulated via the explicit positive semi-definite conditions, which ask that this bunch of localizing moment matrices should be positive semi-definite. So the exact details are not very important. The point is that this moment bound is again expressible as a semi-definite program for any given order. So this was the sum of square bound. So you see in the moment bound, it's L non-negative on the quadratic module. In the SOS bound, it's F minus lambda lies in the quadratic module. So there is this duality, which again, which corresponds precisely to the fact that the moment bound of order t and the SOS bound of order t, each of them can be defined by a semi-definite program. And these two semi-definite programs are actually the dual semi-definite programs of each other. So we have this weak duality. By weak duality, the SOS bound is at most the moment bound, and it's at most the minimum of f. And under, if you assume that the Archimedean condition holds with the ball constraints present in the description of the set K, then actually strong duality holds. So the two bounds are the same. So we have these two dual hierarchies, SOS bounds, moment bounds. So let me now explain what more do we have by looking at the moment side, because it's maybe not yet clear what more do we have. But first, maybe let me give you the underlying principles which give again the asymptotic convergence on the moment side. So this is this pendant of the result by Pütiner, which I mentioned before on the sum of square side. So on the moment side, what Pütiner showed is that if we have a linear functional L, non-negative on the full quadratic module, then L admits a representing measure supported by K. So this gives immediately the asymptotic convergence of the moment bounds to the minimum of f. One important and very useful fact to point out is that if we have a representing measure mu for L, then there is a finite atomic representing measure when we restrict evaluating L at a given polynomial space truncated at a given degree. So this will be very, very useful to have this fact that there is also a finite atomic representing measure when you restrict yourself to a given degree. Yeah. A second crucial result in the moment approach is this result of Curto and Fialco, which underlies the fact that there is an optimality stopping criterion for the moment hierarchy. So what this result is saying is the following. So suppose we solve the moment bound of a given order T, and let L is going to be our optimal solution. So it will be non-negative on the quadratic module. And let's assume that it satisfies this nice flatness condition. So what does it say? It says that, so we have the moment matrix of order T. It contains as a submatrix the moment matrix of order T minus 1, where you restrict yourself to the submatrix indexed by all monomials up to the degree T minus 1 instead of T. So this is a principal submatrix of MT of L. And what the flatness condition says is that these two matrices should have the same rank. And then it's a very nice result that under these conditions, then you can conclude that L actually has a finite atomic representing measure. And this will be a very useful result when applying it to the application to polynomial optimization, because these finite atoms entering the representing measure will actually correspond to the minimizers of the polynomial optimization problem that we are looking at. So let me mention this optimality criterion. So you solve the moment relaxation of order T. I've just repeated the bound. And what the optimality criterion says is the following: let L be an optimal solution to the moment of order T and assume that it satisfies the flatness condition. Then, in view of the result of Kurtoff-Fialkow, what you can conclude is that the relaxation is actually exact. It's not only a lower bound for the minimum of F, it's actually equal to the moment, to the minimum of F. So we have found at order T, we have found the minimum of F. A second second application of the flatness condition is that actually we can also find the global minimizers of the problem. And to do this, what we do is we look at the kernel of the moment metric. So we look at all the polynomials which lie in the kernel. So this forms a set of polynomials. And then we look at the variety. So we look at the set of all their common roots. And the claim is that the variety of the kernel, actually all the points in the variety of the kernel are going to be among the global minimizers. And if we could, if the rank of the optimum solution we had was actually maximum over all possible optimal solutions, then actually we have an equality here. In other words, the global minimizers are exactly the points in the variety of the kernel. And the point is that in the setting where we are, there are actually well-defined linear algebraic methods to recover the global so to recover the points in the variety using the so-called eigenvalue method. So we can compute the global minimizers. So this is this additional feature that I was mentioning in the beginning, that by looking at the moment relaxations, you get additional complementary information about the problem. Namely, you get a hold, or you get a road, which may lead you to extracting the global minimizers of the problem, assuming you have this rank condition, but as shown by some results of particularly by Jiawang Ni, this rank condition actually holds generically, and it holds often in practice. Okay, so this is concluding my general approach on polynomial optimization. Let me just give a few properties. First one is that interior point algorithms actually are going to give this maximum rank optimal solutions, which was nice to have, as I mentioned. Not only asymptotic convergence holds, but often finite convergence holds in several cases. So it holds in particular generically. One can exploit structure in order to speed up the hierarchies, sparsity, symmetry, presence of equations. And the method can also be adapted to find real roots of polynomial equations. So this is a huge topic. So it's a large literature, surveys, monographs, and I will give you a few references at the end. In the last 5 minutes, if I may, I would like to illustrate the moment approach, how to use it to attack the question of giving bounds for matrix factorization ranks. So it looks a priori not really an instance of polynomial optimization, but actually it can also be tackled using this, this kind of method. So this is why I would like to say a few words about that. So matrix factorization, well, so let's discuss, for instance, non-negative factorizations. So you have a matrix A, rectangle matrix with non-negative entries, and you try to write it as a sum of rank 1 matrices. So outer product A, B, where A and B are non-negative vectors. Equivalently, you may try to write A as a gram matrix where the factors U and V are non-negative vectors in a space of dimension R. And then the smallest R, which is either the number of terms here or the dimension of the space here, the smallest such R is the non-negative rank of the matrix. You could look at symmetric factorization when you ask that A equal B or U equal V here. And then you will get the notion of completely positive rank. So the completely positive rank does not always exist because not every matrix has such a nice symmetric factorization. When it has, it's precisely when the matrix is completely positive. And in that case, you are interested in finding the CP rank of the matrix. There are matrix analogs of these notions which occur when instead of having vectors, so oh no, I should look here at the gram factorization. So when you try to find a gram factorization, not by vectors, but by matrices U and V, matrices which are now assumed to be positive semidefinite, and you want the size of these matrices to be as small as possible, and then this R is a PSD rank. And if you insist that the matrices are, if you search for symmetric factorizations, U equal V, then you would get the notion of completely positive semidefinite rank. So these four matrix factorization rank can actually, they are all difficult to compute exactly, but one can, for all of them, one can define good bounds using the general scheme of polynomial optimization. And I just want to illustrate this. So these matrix factorization ranks have applications to extended formulations and to communication complexity or quantum communication complexity. Yeah. So maybe in interest of time, let me just mention very briefly that computing the non-negative rank and the positive semidefinite rank has a direct application to computing the smaller size of extended formulations. So this is this idea that you have a polytope and you try to write it as a projection of another polytope in a higher dimensional space, and you want that this higher dimensional polytope Q has as few facets as possible. And the smallest number of facets is given by non-negative rank of a certain associated slack matrix. It's a result of Yanakakis. And if you want to represent P as a projection of a spectrahedron in a smallest possible, using smallest possible size PSD matrices, and this is a PSD rank of the slack matrix. So it's just to illustrate that these ranks have wide applications. So this is my last slide. So if we want to compute the CP rank, so we want to write A as a sum of rank 1 matrices and using as few as possible. In other words, you want, if we divide by, if you multiply by 1 over R, you are trying to write A 1 over R A, you try to write it as a member of this set R, which is a convexol of XX transpose, where X is non-negative, XX transpose is at most A entry-wise and at most A in the PSD order. So this led Fuzzy and Parrilo to define this parameter tau of A, which is a minimum lambda for which 1 over lambda A lies in this set R, which is a lower bound on the rank, on the CP rank. So this tau parameter can be seen as a convex relaxation of the hard CP rank, which is a hard combinatorial parameter. So this convex parameter is a priori, it's not so clear how would you compute it. And the point is that you can approach it actually using the technology of the MOMt approach. So what you do is you define a linear objective function, a linear functional which acts on the ring of polynomials by, you define it as a sum of the evaluation maps at this AL, which enters the decomposition of A. And then it's very easy to see a bunch of properties. So first of all, if you evaluate L at 1, it's a constant polynomial 1, what you recover is R, the CP rank. So L of 1 gives you back the CP rank. You recover the matrix A by evaluating L at the products Xi, Xj. you can impose a certain, you can impose that L is non-negative on quadratic module generated by certain polynomial constraints which are designed so as to model the non-negativity constraints on X, and the fact that XX transpose should be at most A coordinate-wise. And finally, we only now need a way to encode these PSD constraints here. And here is a possible way to do this. It's a tensor way to do this, or another way to do it is, as we recently found. So in order to get bounds, what you now do is you minimize L of 1 over all linear functionals acting on the space of polynomials truncated to a given degree. And you ask that this L satisfies the truncated analogues of this condition 0, so not 0, 1, 2, 3a, or 3b. And in this way, you get a hierarchy of parameters. Each of them can be computed via semidefinite programming. And this hierarchy of parameters converges asymptotically to this convex parameter tau CP of A. And on the flatness, it converges to it infinitely many steps. So I have described it only for the CP rank for the interest of time, but the same method works for the non-negative rank. You just need to have two sets of variables instead of one. You need the variables X and Y because now it's the asymmetric setting. It extends to the PSD rank, to the CPSD rank, but now you should take the gram factorization approach, and you should use non-commutative variables because you will now have a variable xi to model a PSD matrix. And so this is why you should use polynomial optimization non-commutative variables, but the same technique will apply and will give good bounds. And very recently, we are now working on adapting the methods to tackle how to get hands on the separable rank of a linear operator, which is acting on the tensor product. So how to decompose it as a sum of tensor products of rank 1 matrices, because this is a fundamental question in quantum information. So this is a motivation for looking at this problem. So I just finished with saying that so as I insisted, these two dual approaches via moments and sums of squares provide interesting complementary information. The method I've developed extends to a way more general setting, namely to the problem of moments, where you optimize over measures instead of optimizing over points in the space. It also generalizes to polynomial optimization non-commutative variables, where you may optimize over matrix-valued variables or even operator-valued variables, so no condition on the size of the matrices. And this has many, many applications. And in my next two lectures, I will discuss what about the quality of the relaxations and how to, what about applying the techniques to graph problems. So thank you very much for the attention, and I apologize for being a bit too long over time. And here is a slide with some references.